Hello students, today I will discuss the detailed classification of statistical mechanics. The statistical mechanics is divided into two parts, that is classical statistics and quantum statistics. The classical system or the classical particles will follow the Maxwell's Boltzmann statistics, and the classical particles are called as bosons. So what is the characteristics of the classical particles or bosons? The classical particles are identical, distinguishable, and they are weakly interacting with each other, and they are neutral particles. In statistical mechanics, the Maxwell's-Boltzmann statistics describes the statistical distribution of particles over various energy states in thermal equilibrium when the temperature is high enough and density is low enough. Particle density is low enough. And in that case, the quantum effects become negligible. And another part is quantum statistics. The quantum statistics is divided into two parts, that is Bose-Einstein statistics. Scientists S.N. Bose and Albert Einstein had developed these statistics, Bose-Einstein statistics, in 1924. And the particles which follow the B statistics, Bose-Einstein statistics, they are called bosons. And the scientists Fermi and Dirac developed a statistics, that is Fermi-Dirac statistics, and the particles which follow the FD statistics, they are called fermions. So, in quantum statistics, the Fermi-Dirac and Bose-Einstein statistics can be applied when quantum effects are taken into account or can be taken into consideration. So, what is the quantum effects? The quantum effects appear if the concentration of particles per unit volume, that means N by V, where N is the total number of particles per unit volume, is greater than equal to NQ, where NQ is the critical concentration. The definition of NQ is equal to mkt by 2 pi h cut square whole to the power 3 by 2, where NQ is depends on the masses of the particle. So NQ, that means the quantum concentration, critical concentration or quantum concentration, is fixed for a particular system, but it can be varied for any system to system. So when the concentration of particles per unit volume of any system is greater than equal to the quantum concentration, then the interparticle distance is equal to the de Broglie wavelength. And in these conditions, the wave functions of the particles can be overlapping with each other. Now, in the next slide, I will discuss the characteristics of three statistics. So, first, in the Maxwell's Boltzmann statistics, the particles, that means the bosons, the particles are identical and they are sufficiently far apart to each other. So, they are distinguishable. The example of classical particles or bosons are ideal molecules of gas. As they are sufficiently far apart with each other, their overlapping of wave function is negligible, and they are neutral particles, so they do not possess any kind of spin, and any particle can stay in any energy states for classical particles. And in case of Bose-Einstein statistics, the particles are called bosons, and the example of bosons is photon, phonons, etc. The boson particles are indistinguishable, identical, and they possess zero or integral spin. That means their spin angular momentum ms h cut is equal to 0, h cut, 2 h cut, 3 h cut, and so on. And for the bosons particle, there are overlapping of psi wave function and they have symmetric wave function and they don't obey the Pauli's exclusion principle. In case of fermions, they are also indistinguishable and identical particles, but they have half integral spin. That means ms h cut is equal to h cut by 2, 3h cut by 2, 5h cut by 2 and so on. They are half integral spin. And the example of fermions are electron, proton, neutron, etc. Fermions obey the exclusion principle and they have antisymmetric wave function. Now I will discuss what is Pauli's exclusion principle. In quantum mechanics, Pauli's exclusion states that the two or more identical particles with half integer spins cannot occupy the same quantum state within a quantum system. Here, the half integer term is very much important because the half integer spins corresponding to the fermion and only fermion particles can obey Pauli's exclusion principle. So here in this statement, the half integer spin term is very much important. So in this figure, we will say that the two spin up or two spin down particle cannot occupy the same quantum state. Only one spin up and spin down particle can stay in the same quantum state. Now I will come to the statistical distribution. That means how the particles can be distributed in a system. Suppose there is a system where n number of particles are present. The n is constant for this system and the system is in the thermal equilibrium at absolute temperature T. And there are a certain amount of energy E is distributed among the n number of particles. E is the total energy which is also constant. So, suppose there is a n1 particle in the G1 number of energy states, n2 particle is sitting or occupying the G2 number of energy states and n3 particles are occupying the G3 energy states and so on. So, the number of particles, that means n, can occupy the G epsilon number of energy states into the distribution function. That means the particles can be seated in the number of energy states according to the particles nature, whether they are classical particles or they are quantum particles, that means bosons or fermions. So, suppose the n epsilon is the number of particles having energy epsilon, then n epsilon is equal to g epsilon into f epsilon, where g epsilon is the number of states of energy epsilon or the statistical weight corresponding to energy epsilon. The g epsilon is also called degenerate states. That means the number of energy states having the same energy level. And the number of energy states, that means G epsilon, per unit energy interval is called density of states. And F epsilon is equal to distribution function. That means average number of particles in each state of energy epsilon or the probability of occupancy of each state of energy epsilon. Now I will discuss the Maxwell's Boltzmann statistics. That means in a classical system, how the classical particle or bosons can be distributed in a system, classical system. So, according to this Maxwell's Boltzmann statistics or distribution law, the identical and distinguishable particles are present in a system at temperature T having energy epsilon. So, we now apply MB statistics to find out the distribution of energies among the molecules of an ideal gas. In the quantum system, we are considering discrete set of energy. However, in a classical system, we are considering a continuous distribution of molecular energies instead of discrete set of energy. Suppose there is this, in number of particles, n epsilon is number of the molecules where energies lie in between epsilon and epsilon plus d epsilon energy states. So, as discussed in the earlier slide, we can write n epsilon d epsilon is equal to g as a function of epsilon d epsilon into f epsilon, where n epsilon is equal to a into e to the power minus epsilon by kt. That means average number of particles in each state of energy epsilon. This equation A represents the Maxwell's Boltzmann distribution law. However, this Maxwell's Boltzmann distribution law is valid for classical system or classical statistics. That is why this law cannot explain the behavior of photons, because the photons are the boson particles and the electrons in metals, because electrons are fermions. That is why the behavior of photons or the electronic properties or electrons properties cannot be explained by Maxwell's Boltzmann statistics. Now, in a classical system or classical statistics, Ni by Gi, Ni is the number of particles can occupy the Gi number of states, is very less than 1, because in a classical system the particle density is low. That means the particle density is very low with respect to the number of energy states. That is why the particles can be treated as distinguishable and they are far apart with each other. And that classical distribution is valid for dilute gases. Now I will discuss what is the total probability or thermodynamic probability, that is called W. That means the number of microstates for any given macrostate for any classical system. So, suppose there are total n number of particles can be present in a system, classical system, and they can be grouped into the level having n1, n2, n3 and so on. So, the number of particles, number of ways in which Ni particles can occupy the Gi sublevels is Gi to the power Ni, and here total n number of particles are present, and their n1 particles are alike and n2 particles are alike and so on, and they are distinguishable. So the total probability W can be written as W is equal to n factorial into Gi to the power Ni by Ni factorial. So this is the thermodynamic probability or number of microstates for any classical system. Now in the next slide, the first picture is corresponding to the, suppose there is a gas molecules and they are randomly moving in a system, and the next the down picture is corresponding to the simulation of the 2D gas reduction towards a Maxwell's Boltzmann speed distribution. What is that? That means the particles are constantly moving with respect to the time. So in the in this graph, the particles velocity and speed is continuously changing with respect to the time, and there is a probability density with respect to the speed. Now in the right side there is a graph which is plotted Maxwell's Boltzmann molecular speed distribution for noble gases. We already know that the most probable speed of the gas molecules is proportional to the 1 by root over m. M is the mass of the atomic molecules. So in this graph we have considered 4 noble gases, that is helium, neon, argon and xenon. The atomic mass of helium is around 4, neon is 20, argon is 40 and xenon is around 132. So for helium gas, the most probable speed will be maximum, as helium has less mass. So the blue curve denotes for the speed distribution of helium gas, and this is the curve is broad. Whereas for the xenon gas, which is denoted as a purple color, which has higher mass or highest mass, that is around 132. So for the velocity, most probable speed is least. That is why the probability distribution, the Maxwell-Boltzmann molecular speed distribution for the xenon gas will be sharp, and the neon and argon graph will be in between xenon and helium. So this is the Maxwell-Boltzmann molecular speed distribution for the noble gases, how they are changing with respect to the particle mass. Now I come to one problem which is based on the Maxwell-Boltzmann statistics. What is that? At what temperature would 1 in 1000 of atoms in a gas of atomic hydrogen be in the first excited energy level? That means that there is a system that is atomic hydrogen, and where in a ground state thousands of atoms, ground state means n equal to 1, thousands of atoms in present. For that thousand of atoms, one atom will go to the first excited energy level, that means n equal to 2. At what temperature? At what temperature? From the 1000 atoms, one of the atom can go to the n equal to 2 state. So let's see what is the solution of this problem. For the ground state, that means n equal to 1 state, there is a 1:2, that means the number of energy state will be 2. And for the first excited state, that means n equal to 2 state, there will be 2:2p6. So the total number of energy states will be 8. So using the Maxwell-Boltzmann distribution law, we can write that NE2 by NE1, that means 1 by 1000, is equal to AGE2 into e to the power minus E2 by KT by AGE1 e to the power minus E1 by KT. We have just given the value of GE2, GE1, E2 and E1. E2 for hydrogen atom is equal to minus 13.6 by n square. That means minus 13.6 by 2 square, and E1 is equal to minus 13.6 by 1 square. And putting all the value, we can estimate or we can measure that, we can find out that T is equal to 1.42 into 10 to the power 4, where the K is the Boltzmann constant, which value is 1.38 into minus 23 joule per Kelvin, and we have to convert EV to joule, that means 1 EV is equal to 1.6 into 10 to minus 19 joule. Putting all these value, we just calculate the capital T, which is 1.42 10 to the power 4 Kelvin. Now, using the Maxwell-Boltzmann distribution law, we can find out the Maxwell-Boltzmann energy distribution curve for the molecules of an ideal gas, and this curve is not symmetric in the both sides. Now, using the Maxwell-Boltzmann speed distribution, we can find out the most probable speed of gas molecules, average speed, and root mean square speed. The most probable speed has less value, then the average speed, and after that the maximum speed, that is root mean square speed of any gas molecules, and the speed distribution is not symmetrical. After that, we have explained how the molecular speed is varying with respect to temperature and molecular mass. As we already know that the most probable speed is proportional to the 1 by root over m, and the most probable speed is proportional to the root t. That means when the temperature is increased for a fixed molecule, that means here oxygen, when the temperature is increased, that means the most probable speed is also increased. So in this case, the for oxygen molecules at 273 K, the molecular speed is around 1500 meter per second. So there is a broad distribution, and at the lower temperature, that means oxygen at 73 K, the speed distribution will be sharp because their speed distribution will be less. So now we explain what is the limitations of Maxwell's Boltzmann statistics. Here we have considered that the particles are assumed to be distinguishable, although many elementary particles, the electron protons, they are indistinguishable. So there is a limitation, and there is another limitation is in these Maxwell's Boltzmann statistics we have assumed that any number of particles can occupy the same quantum state, or any state can accommodate any number of particles, while for fermions they obey the Pauli exclusion principle. So these are the limitations of Maxwell's Boltzmann statistics. Thank you. This lecture is ended here.